Oh god. I went to go switch my scene and I almost turned off the stream. Oh, hey, Scribble. What? Hi, what's up? POV what? I legit just opened Twitch to see if it was on. You can always count on that. 3 p.m. damie stream. Classic damie moment. Me going, I'm gonna stream at 2 today, and then I'm like, no, it's gonna be 3 p.m. Whoopsies. That's why I don't have a stream schedule. I'm normal. Anyway, sorry for the green, but I was, the universe foretold. That was my magic. I was casting magic. I was doing this problem earlier because I goofed it really bad. Well, okay, I didn't goof it that badly on my exam, but when I was doing it, I was just like, I was like dumb, or I'm okay, dumb is maybe mean to myself, but I was, I made a bunch of reading errors. Like I was reading it like this, and I was setting up equations, and I was like, what was I doing, dude? Anyway, I did it. I think it's 175. I don't know if it's right or not, but I think it's that. Anyway, that's not what we're doing. We're not doing green today. We're gonna do work and energy, which, you know, that's fun. It's exciting. I think I'm gonna use like a brown pen. I'm trying to use more fun colors because I've been only doing like, I've been doing like, you know, what? Gray? That's boring. I can have any color I want, and so we're gonna do that. But okay, let's start with some concept stuff. I'll do one at a time. I have a lot. I don't know. I think. Okay. I did get after we figured out that like you do the every acceleration in terms of alpha, and then you just get rid of everything to solve for alpha. Then I got everything. I was drowning in the sea of variables, and I didn't know where to go. But let's see if that is going to happen also with this one. I don't know. It probably won't because it's work and energy, but we'll see. We'll strive for. My Windows taskbar crashed. Oh no, it did. Never mind. We'll strive for an ingredient list for the potion we're gonna make. Okay. A round object of mass m and radius r is released from rest at the top of a curved surface and rolls down without slipping until it leaves the surface with a horizontal velocity. Will a solid sphere, solid cylinder, or a hoop travel the greatest distance x? Okay, so this is a question about moment of inertia. Okay, there's a couple things we need to know. Is that there's going to be work and energy, so let's just write out the work and energy equation. So delta t equals delta Vg plus plus u 1 to 2. So there's no, oh god, the battle music. There's no spring potential, right? No elastic potential, so we don't have to worry about that. And we start, so let's just write this out. So T1 plus Vg1 equals T2 plus Vg2 plus u1 to 2. So in terms of if we have different equations here, these are both going to be, so this is going to be the same. These are both going to be the same because they're just based off of mass, right? And they say that they say a round object, so they have the same mass, all of them. And the thing is that because they have the same mass, the friction is also going to be the same. And we do have to know that there is friction because it rolls without slipping. So that's the key bit there, because if it's rolling without slipping, it means there has to be friction. So that means that leaves us with T1 plus like C equals T2. That's an I. T2. That's a C. What am I doing? Writing. There we go. So T1 is going to equal 1/2 mv1 squared. Well, this is 0. Okay. Don't worry about that. So we have T2 equals C. This is our comparison. So whichever has the biggest T2 in terms of variables is gonna net us our our thing. So we'll have 1/2 m v squared, v2 squared, plus 1/2 I bar omega squared. Let me check that. immediately an issue. I don't remember if there's an alpha in there. I want to say there's an alpha. I want to say it's I bar alpha omega squared, but I know there's an omega squared. This is like 1/2 mv squared. 1 second. I'm checking my tomb of books. Where are we at? I'm looking with my big eyes. No, it's just I bar alpha. I bar omega. Yeah, because we don't actually care that much about accelerations in work and energy. Well, okay, maybe that's a lie. Yeah, no, that's kind of true. We care about velocities. Okay. So these are all going to equal each other. So let's just say v2 squared equals my mentality. If a program has been made to calculate this, use that. If not, make the program. So like I made a program to help with, it's really easy to make a program to like do these things because it's just like algebra, right? Like I just use MATLAB and like you can just put in equations and stuff to it. But you still have to like identify all your variables and stuff. And in this case, this one would probably be harder to do with a computer than doing this out, because you would have to do all this anyway to see what it would be, you know? Or maybe you don't know. So v2 squared. This is really like an arduous way of doing it. I could just instantly say, okay, whichever has the biggest I bar is going to have the biggest. Make an AI. Ew, no, AI is bad at things. That's gross. C minus I bar alpha squared. AI is actually genuinely pretty bad at things. Make a good AI? I mean, a good AI is just an algorithm. My hot take. So as I bar goes up, V goes up, V2 goes up. So I guess we just need to figure out the biggest I bar, which I think is solid sphere, solid cylinder. So I bar sphere. I think it's the hoop. Impossible. AI is just like not good at doing like the way that our AI works now is like, is this multiple choice? Yeah. You still have to prove it. Let's see, solid I bar for a solid sphere. Oh, what is it? 2/5 mr squared, 2/5 mr squared, and then I bar for a cylinder, I think is 1/12 ml squared. Ugh. Wait, we don't know how long the cylinder is. I get 1 mark on this test. Oh, no, the whole thing is not multiple choice. There's like, on the actual exam for like the final, there are some multiple choice questions, but they're mostly conceptual. Like something like this is like a conceptual question. For a solid cylinder is, I think it's dependent on L, which is not particularly fun. Oh no, it's MR. Whew. Whew. Okay, so 1/2 mr squared, so that one's bigger, and then I bar for like a hoop, right? I already forgot, what was the third one? A hoop. I'm pretty sure it's a hoop. What is... It's not giving me a moment of... Oh, something is lagging my computer the hell out. What the heck? I don't have anything up. Okay, well, whatever. I get 0 marks. Well, I mean, it would be pretty hard if you didn't know dynamics. Area moment of inertia. Hoop. 1/2 m a squared plus b squared. Yeah, it's bigger. Is A, yeah, A squared plus B squared, yeah. Hoop equals, I mean, because if we think about it, a moment of inertia is like how much it's going to roll, right? If you have a bunch of mass around the outside of it, it wants to roll a lot more. So, a hoop. But the reason we have to do this outright is because we could say, like, this is a very common question to ask. We could say that, oh, well, we know that the I-bar of a hoop is biggest, the area moment of inertia, and so that means it'll go the farthest. But just in case, I think it's good to do the math out to just say, like, oh, well, we know that this is proportional because it's on the top. I think it's just good to sanity check that, but it's also good to, like, be able to recognize why that's the case. All right. Okay, this is the same kind of thing, I think. Maybe? Maybe not. Ooh. Okay, let's see. I wrote so much for this, I really didn't need to write that much for this one. I'll put this one on the bottom, but I'll have to split the other one into two, I guess. Well, I can be a little more, a little more efficient. There we go. Put that up there. Oops. There we go. Sorry, me being a wizard and moving around my layers. Okay. Okay, a solid steel sphere. Great. Of radius r minus m is released from rest and rolls without slipping, without friction. After traveling a distance d, it has speed v. Okay, this is great. This is great. I love these kind of questions. All right. So we know that, okay, so the delta t equals okay. How do I want to say this? I'm thinking ahead too much. Let's get it down on the paper first. Okay. So for case 1, let's start with that one. So it's 0 plus vg or mg. I'm gonna define something as h because we're gonna compare these. So it doesn't really matter what the height is. It just matters that they move the same height. Equals, I'm gonna put my datum here. So then we have 0, we have t2 plus 0 plus this. So u1 to 2 prime is going to be based off of... let me write out t2 a little bit more, actually. This will be 1/2 mv2 squared. 1/2 mv. Okay, so this is v, right? So it has a speed v. V squared plus, and the I bar alpha is also going to be the same, but that's no, it's not. I lied. Don't listen to me. 1/2 alpha omega squared. Omega squared is going to be the same. Okay, so now if we compare to 2, we'll have mgh equals 1/2 m v b, I guess, squared plus 1/2 I bar, so this will be a b omega squared plus u1 to 2. So all the things that don't have subscripts on them are the same. Because they're going to move the same distance, they're going to have the same friction. Actually, wait a second. No, it's okay, it has the same mass. Oh. Whoa. Okay. So we know that the I bar of a sphere equals 2/5 m r squared. So I bar A equals that. But I bar B equals 2/5 m 2r squared equals 2/5, like 4 I bar A. Right? So the idea is that the difference that the velocity is going to be is going to equal, we say 1/2 mv squared minus 1/2 mvb squared equals the difference in the I-bars. So it's going to be 3, I guess 1/2 times 3 I-bar a omega squared. Okay, I can get rid of all these. And I can't get rid of the m's. That's going to be v squared minus vb squared equals 3 times... okay, so now the weird thing is, like, the omega is going to be the same. Oh, but we can turn that into VR. Oh, exciting. This is a little jank. I might have to redo the math on this one, depending on how this shakes out. Okay, so I bar a is 2/5, and it's going to be r squared, because I got rid of the m, and then we're going to multiply that by v squared over... Okay, omega equals like v times r, so v squared r squared. We're still okay. But it's not great. No? It's okay, I think. So we get vb squared equals 3 times 3/5 times r to the 4th minus 1. I'm gonna switch that. Square root of that times v. Now, that equals r squared. Okay, that's not good. We have like an r in there. But we're on the right track, because we do have a v. Okay, let's maybe let's change this. Let me change this. Okay, what do we know equals each other? We know that the mgh's equal each other. And the ugh's is equal to each other. So we say 1/2 mv squared plus 1/2 I alpha, that equals 1/2 mvb squared plus 1/2. Okay, I'm gonna get rid of the 1/2s. Look, that's annoying me. Okay, I got rid of the plus. Wait, what did I erase? Oh, okay. This is confused. Plus I bar omega squared. Okay, maybe we'll just do it symbolically for now. So mvb equals m v squared plus I bar alpha omega squared I bar alpha minus I bar a minus I bar b omega squared over m. Okay. This is a weird thing that exists. We're getting closer to something that exists though. Okay, so I bar alpha minus I bar beta equals, I don't know, -3 I bar alpha. Do we want that, or do we want, I mean, let's do this one. But like, we're not getting rid of an R. Okay, maybe. Nope, it's because I goofed. Wait, we're winning. Don't worry about it, chat. Don't worry about it. Okay, the plus is a little scary though, because that's... Hi Umbra, how's it going? Plus is a little scary, but I'm gonna keep pushing forward. R squared times b to the 4th over r squared. Oh no, we can factor. Oh, we're winning. I think we won. V squared Maybe we're not winning too much. Okay, v squared minus 6/5, v to the 4th. Is it? Wait, no, it should be... What does omega equal? I think it's v squared over r, right? Or is it v over r? Huh? Wait. V equals omega r? V equals omega r. Omega equals... No, we're winning. It's not to the 4th. I'm goofing. I'm a goofer. Oh my gosh. Wait, 1. So 1 minus 6/5 is 1/5. It's the square root of 1/5. What? I don't know about that one. What's the square root of 1/5? It's not like 0.5 for sure. Is it because like v equals like... V equals some stuff anyway, and so like if I do this, then it's not like a true... Wait, maybe I don't subtract them. Wait, yeah, maybe I just don't subtract them. Would I do that? What would that do? I don't make the difference. Well, I just set them equal to each other to say like MGH equals MGH, which is true. I just set it up in VB equals... No, I can't do that. I have to set them equal to each other. In my brain, I'm like, wait, okay, what if I don't... What if I just said it was 4? Because then it would be square root of 1 over 4, and that would be 1/2. You know? But I feel like that's... Because I bar alpha minus... Wait, that'd be 5. Wait a second. Wait, am I? Wait. 2, 8... No, I didn't subtract wrong. Oh wait, it's B minus A. Oh wait, it's B minus A. Right? No wait, it's not. It's A minus B. What? Also, I don't think that would change anything. It would just make it positive. What is I feel like it's supposed to be 4. Okay, like 4 is this thing we're supposed to get, not a... What if it was 1 plus that? That'd be 11 over 5. That's also not the correct thing. Oh, I'm so close to this. Maybe my wizard powers aren't working. Huh. I want it to be 4 so badly, but how could it be 4 if you do the math and it's not 4? But all my intuition is telling me it's 4. What if I just said it was 4? Like for fun, you know? If it's 3, it's so... Wait, but it has to, but the over 5 is the thing that's the issue, actually, not the 3. Unless it was, well, 15, what would it have to be for 15? Because then that would divide, but then it would give you 3. That would also be bad. Let's see. If I was gonna do this, if it was square root, it's definitely not 0.25, because that would be like a lot. I'm just trying to think what you'd have to get 5. You'd have to get 10 up on top. It was 4 plus 6. If we had like 2 IA bar, that would give us... No, because everything has a 1/2, so I can get rid of the 1/2. Maybe if I just say, what if I say this? I say 1/2 mvb squared equals proportional to I bar 1/2 or I bar alpha. What about that? What if we say proportional? Is it even, it's not even proportional. That's just a lie. I can't say that. Wait, but my brain, it's so... Because you add them, you subtract them, and then they go. Wait, but if I subtract them... No, I'm not actually subtracting them. I'm just setting them equal to each other, and then I'm crossing stuff off, so I don't need to worry about negatives. This is so strange. You come here to witness strange oddities happen in the mathing world. Well, this sure bodes well for the rest of the case. I'm gonna put a star on this. We're gonna come back to it. I'm gonna put a question mark on it, actually. We're gonna come back to that one. I was so close. I just can't get the last little bit there. Okay, well, let's... Maybe the divine inspiration will strike me when I do a little bit more of it. That's so... I've done a problem like exactly like this before. Like, it was 3 years ago though, so... Oh, let's see. Okay, slender bar A is rigidly connected to massless rod. Massless rod. Interesting. The vertical thickness is negligible compared to A compared to L. In both cases, A is really... Okay, it's about centroids. So this centroid is at... I don't know. Gotta do some math. Let's see. So it's gonna be cos theta. Let's call our datum here. Let's call our datum here, because I don't want to do more math than I have to. So this is gonna be... Also, I guess let's just, like, for argument's sake, let's just say that this is whatchamacallit. Also, this is the length L, by the way, too. Let's just say that this is like a line, and that this doesn't have any thickness, so we don't have to add the thickness. So we're gonna say L cosine theta is the gravitational potential of that. And in this case, centroid's here, and visually it looks, you know, whatever. This is also length L. I think it's the same. I think they would be the same. It's a massless rod is the thing. If it wasn't a massless rod, then the centroid would be moved up a little bit, and then it would have more kinetic energy. But I mean, they're both being lifted up to the central. If we assume the centroids are, I mean, in this case, it would be like L cos theta. In this case, it would be L cos theta. L cos theta plus. We would say this is d over 2, so like d over 2 cos theta. And that would be maybe bigger, but I mean, actually, no. If we could, I mean, it says it's a slender bar, so I assume that means that we. Yeah, it's okay. The vertical thickness is negligible, so that would be. I mean, that would be the case if it wasn't negligible, but I think it would be the same, unless. Well, I mean, what else would you have in terms of energy? They're both released from rest, so it's 0. Gravitational energy is what it is. There's no like. Is there work being done on it? Wait a second, there might be work being done on it. Let's think. Oh, also maybe I bar is different. Oh, wait a second. No, you know what it is? Oh, that's what it is. One's rotating and one's translating only, so that the oh god. Okay. But it's larger kinetic. It's not asking about like larger rotational kinetic energy or whatever kinetic energy. It's only asking about kinetic energy as a whole, which they would have the same amount of. But if they said which has larger like translational kinetic energy or something, which has a larger velocity, then case 2 would be higher, because it's not rotating, so none of the kinetic energy is lost to rotation. Whereas for case 1, it is lost to rotation. Some of it is like put into it rotating the bar. Wait, but it's fixed axis rotation, so it's not wait, is it translating and rotating? Wait, let me think. Oh, that's what it is, because 1 is. Oh, okay, so case 1, t equals 1/2 alpha omega squared. For case 2, t equals 1/2 mv squared. Oh, they're sneaky. Okay, so this is gonna equal. I'll put it in terms of v. So we have slender bar is 1/12 ml squared. Which would, be something, and then we'd have v squared over r squared. R is L, I guess, L squared. Oh, no, I can't use L. Wait, what is the length bar A? I guess it doesn't really matter. It kind of does. They both have the same length, but this one isn't dependent on the length. And we'll just see what the it kind of does matter. It's okay, wait, slender bar. Yeah, it's based off of the length. I'll call it L like this. We'll call it L like that. So this is gonna be 1/24 v squared. So the m's, okay. Let's say t1 to t2. That's 1/24 L squared over L squared. Little L squared over big L squared. And on the bottom we have 1/2. And everything else goes away. I guess I should probably say v1. Yeah, the v's aren't the same, potentially. L squared and then v2 squared. I don't really know what that tells us, actually. This it's not very useful. I was thinking, oh, the v's will cancel out and we get a fraction. I mean, I guess but the v's aren't going to be the same. We can't assume that they're going to be the same. See, I'm not really sure because, like, one of these is dependent on think it's dependent on how long the bar, like if you had a really long ass rod and it was rotating, then yeah, it's gonna like, if it was super long and it was being raised at an angle, then you're gonna lose rotational energy. But if you have a really long bar, if you have a really long bar for A, it just has a huge mass and just like so much energy that it like would possibly win out. I don't know about this one. This one is weird. It doesn't say anything about about the length of the bar. But the thing is, like, the case 2 is not dependent on the length of the bar, because it's not rotating. So let me think. This is so goofy. Unless I'm making my I-bar up wrong. I'm like, unless I'm making it up instead of using the correct one. ML squared. It's ML's, right? I'm looking it up. I'm pretty sure it's right. Okay, the kinetic energy won't be the same though, for sure. But like, doesn't it depend on the case? I-bar for a slender bar. I know my I-bars. This is so funny. Wait, so if you had like, you had this. Okay, you had really short ones, and you had like a long bar like that. And then you had a really short one, and you had a long bar like this. Like, yeah, it's gonna rotate a lot more. Wait, sorry, not like that. Like this. Wait, no. Sorry. I'm trying to draw this correctly. Like this. It's gonna rotate like that much, which is like a lot of rotational kinetic energy. You know? But it's not gonna have that much I feel like this is, I guess we kind of just have to go with like the case that they gave us, which would probably be case 2. Because it looks like L is longer than, if L is longer than little l, then, let me also define this as little l. Then this number would be, so like if L, let me do this. L is considerably smaller than L, then L over L equals like, okay, we'll just say like equals like a fraction, like 1 over L. I mean, it would equal 0. Really? Why is my music stopped? Is this blocking? Yes. Hating on me. It would equal 0. If the length was too long. Wait, does that make sense though? I mean, no, because like, but it's still gonna have, oh, because they both have gravitational potential, which is the same, and it's getting turned into this. So it can't be 0. That would just not be possible. It would be like very small. 0.01 like something. I'm gonna say case 2 because I feel like that's where we get with that. But the second one, I feel like that's important to note. Unless I'm just like missing something. I'm probably just missing something about it. Wait, let's see if we can find this. Because I'm actually interested to see if I'm missing something. What was this? What does this say? Let's see if I can. Okay. And chords in case 2 as shown the typing ASMR. It equals 0, which will have the large. Okay, that was like a lot of typing. I did not need to type that much. Let me see if I can just like actually snag it. I don't know if that's. I don't know if that's true. Let's see. Okay, never mind. I'm gonna change my method slightly. Oops, that's not it either. I'm just opening up random files. You know how it be. Oops. What is it? 16? 17? I love that. Oh, I'm so forever thankful that. Oh, thank God. Okay. The kinetic energy will be the same. No. Wait. I just did it for the velocities. That's not the kinetic energy. Fuck me. I just found whether the velocities would be bigger or not. Right? Bro. The whole kinetic energy just equals mg. There's nothing else for oh my god, oh my god, oh my god, I'm going insane. Okay, well, I figured out the velocity thing. No, yeah, no wonder it didn't make any sense why they didn't give us any lengths or anything at all. Oh my god, I hate everything. Oh, okay. Peace of mind for you guys. That's why it's that. I'm so... That's insane. Okay, well, teehee. Teehee. Okay, wait, there's another question. Wait, that's the same question again. Wait, no it's not. Oh. Wait. What? Is this not, this is what? Wait, I'm confused. This looks like the exact same question again. But it says that it's a different question. Oh, this is a great song. This is a different question, but there's one lower that looked like exactly the same question, but it said, I don't know. The speeds of the centers of gravity. Okay, this is what I just did. That would be case 2 would be larger. Because the other one, right? Let's think. The speed for case 1 is going to be tangent to the circle that it's moving about, which is omega r. And then speed for case 2 is going to be also tangent to the circle. True? No, it's gonna be tangent and like a little down, I think. I think case 2, because we did just do all the math for that. If it's not right, well, I'm gonna be sad. Let's see though. I'm very curious. Oops. Case 1 has rotational kinetic energy, so it's smaller. Okay, good. I mean, we just proved that, but like also, you know, whatever. Because for this one, whoops, I'm just like zooming in on it. Does it have, so the thing is like, does it have translational and other kinetic energy? That's the one that's weird. I think yes. Because like, if you have, it just feels weird because like you're including omega twice. I mean, I get why, because like energy's going to rotate it. But like, in your V, sorry, I'm like looking, I'm staring off into the distance. In your V, you have V's omega R. So like it's all from omega. So yeah, it has, I guess it has, let me write a little note. Let's write a little note in the margin here. Fixed axis rotate equals has TL. I think I'll know what that is, and rotate. Odd. You wouldn't think it does, but well, but I guess because like if you're just moving in one place and not changing your center of gravity. Oh, that's what it is. I'm gonna say like pure rotation. Like a pin here. Pure rot equals V for V equals 0. But if you're like swinging about something, right, this is rot plus move, or plus TL. That would have been, you know, nice to just like say at some point when we did this, but okay. I mean, it's not that hard once you think about it for like a little bit, but like, I put the cart before the horse a lot in dynamics. You know how it is. Okay, let's see. What have we got? What other tricks and okay, this is the same problem as the thing. Sorry, let me like zoom in over here just so I can make sure this is the exact same problem. I'm pretty sure they just put the same problem twice, but they like changed the... Wait. What's different about this? Oh, it's going from the bottom up. Never mind. Okay, I lied. T. Which system will have the largest kinetic energy? Okay. Okay. Wait, it's released from rest at an angle of 0. What? How would it get up there is the thing. Is it just like being picked up? I mean, I guess we say... I mean, have 0, 0 equals, is it not the same thing? Maybe because if it starts at 0 and we just go up, they're both... Well, which one will have largest kinetic energy? How does it get up there? Wait, what? I'm just confused. Oh, maybe... Oh, when is it like swinging past, maybe? Maybe that's what it is. Oh, I see. Okay. Yeah, let's say they're swinging past. It would have been nice for them to say, like, hey, it's... Maybe it's here. It's either here... We'll just say it's that, just for my state of mind. Or I guess that's theta O. Like that. And this is theta that. That's a weird... That's unfortunate. Okay, that's fine. Okay, which will have the largest kinetic energy? So the change in gravitational potential is going to be the same. But... Would it not be the same? I don't know. Let's think. Unless I'm misunderstanding again. But when they don't label theta as 0, it's kind of hard to tell if they mean like the other side or something. Let's see. I would say that it's the same thing as the other one. It's released from rest and if the angle theta equals... Okay. The largest kinetic energy. What else would they have? I guess it depends on their... But their change in distance is going to be the same too. I mean, it's going to be like L cosine theta, theta naught minus L cosine, or yeah, minus L cosine theta, theta, I guess. The second angle. Why would there be a difference? Let's see. No mass list, no. Again, it's kinetic energy, so it's not just changing. There's no spring potential. There's no work, okay, work being done by non-conservative forces. I mean, I guess there's tensions in both of them. Oh, is that why? Because the work done is larger, but that doesn't make any sense. They're not the same mass. I don't know. Let me see. Let me see if I can figure out what they're trying to say. What? Wait, I'm losing my mind. It's saying it'll have a greater change in gravitational potential energy. Why would it have a greater change in gravitational potential energy? Oh, is it because I'm just doing my... This is L, and this is L. Okay, I don't see how they would have a different change in gravitational potential energy. If it's... Oh wait, it's not negligible. Oh my god. Okay, well we did the math for that. That's yeah, d over 2 cosine theta. Oh, that'll make it smaller, and then it'll have... Okay, fine. Case 1. It's L minus L cosine theta minus L... Oh, sorry, theta not. L cosine theta plus d over 2 cos theta. Not. And this is L cos theta. Loss L cos theta. Not minus L cos theta. That. Yeah, and that'll be smaller. Or it'll be bigger, I guess, because it's up higher before something. I don't know. Man, that's frustrating. Okay, well, reading. Is that right? Actually, wait, let's see if the math, that is right. It would be L cosine theta for the first one, and then minus no, it would be L minus L cosine theta. Or wait, no, let me make my my datum the top. So if we say this is the datum, so how far this is up here would be here, so that's L. L cosine theta. Wait, is that cosine theta or sine theta? It'd be cosine. Okay, cosine theta, so this one would be L cosine theta plus a little bit, which would give a bigger change. Yeah, that's what it is, a bigger change in potential. And then the signs would work out so that it's like a negative velocity or whatever. Yeah. Good. Okay. Man, that's so annoying. They switch one word, and I'm like, it's the same problem. Fine. Alright, finally an actual thing we can do. Actual problem. Let's see. Oops. There we go. Alright. Disk A is at rest when placed in contact with belt BC, which moves to the right with this constant speed. Knowing that the friction is that, determine the number of revolutions executed by the disk before it attains a constant velocity. Okay. Woof. So we're trying to find, what are we trying to find? We're trying to find like a distance, or we're trying to find like a theta. Which I guess we can figure out by saying, by kinematics after we get a velocity. Because once we know the constant velocity... Ooh, this is like a lot. Okay, well, what do we start with? I guess different states? That's a work and energy thing. So at the first state is gonna be, I guess... Oh, but also, what do we include in the, oh my god. It also gives us a weight, which makes me think we need FMA. Well, I would assume maybe the first state is the zero. State 0. Yeah, let's start with that. Oh, no, you know why it gives us the weight? We do need to do FMA for the friction. That's fine now. We don't have to worry about that. Or, I mean, we'll get there. So work and energy. So state 1. V equals 0. State 2. V equals const. All right. So how do we get from state 1? So state 1, delta VE is not gonna do anything. Delta VG is not gonna do anything. U1 to 2. Friction is gonna start this thing moving. Which makes sense. So T1 equals T2 plus U1 to 2. And U1 to 2 is going to be negative. Is that true? No. Maybe. U1 to 2 is going to be, let me think about that. So if we have T1, no, it's going to be positive if it's over there, but it's going to be negative, and then we'll have, that's a little weird. I'm trying to like force a sign on this thing, I think, that doesn't want to be forced. Let's see, so T1 is going to be 0. I mean, T2 is going to equal U1 to 2. Doesn't really matter the sign right now, because we'll have to figure out the velocity and stuff, like which way it rotates. I mean, it's not like it's gonna pull this way, so it's gonna rotate this way, right? Also, it's gonna be an angular, it's gonna be pure rotation, which is exciting. So let's maybe put that in. 1/2 I bar omega squared equals, and in this case we have the integral from S1 to S2 of f dot ds, which is a fancy way of saying ff times distance. Now we're gonna have to do some relationships to get the omega in terms of distance, I think. That's why we have that v constant. We also need an ff. We'll do some FMA over here. Pop this down here. Here's our, I guess we'll have an I bar alpha too, huh? Ooh, that'll be interesting. This is mg. N. And which way does the friction go? So let's try and see. We have a force that's pulling it that way, so the friction has to pull it this way. Is that true? Actually, I'm not sure. Wait a second. Would that be true? If I had something moving this way, let me try and figure it out. If I had something moving this way. No, I think it's gonna go the other way. No, it's rotating down, it's rotating down. Me just like taking my pen and going like, if I move my hand, it rolls down. Yeah, so it's gonna pull. I mean, I guess the only way you can do that is if it's traction, FF. That's the only way the friction can move it forward. And then this is the MAD. Wow, that's a... I'm just gonna assume I bar. No, I'm gonna not assume that actually, because we do. Wait, no, it is this way. Wait, what am I doing? It is this way. It's rotating that way. It's got to speed up that way, so. Do we say? What do we say? Oh god, okay. Wait, but there's another. Oh. X is 0 is the thing. And MAY is 0. There needs to be some sort of... No, I think it's okay that we don't have those, because we're gonna say that FF is equal, like the moment of FF equals alpha. But I feel weird that we don't have another force opposing it, so there's a normal force. Lol. This is like normal pin. This is normal belt. Okay, sum of equals 0. Do that. we have NB minus mg equals 0, NB equals mg. And then we have the moment about g equals I bar alpha. Yeah, so we say ff times r equals I bar alpha. So that's mu sub whatever k? No, s. That would be, actually, that would be, I don't know what subscript that is. Can anybody read that? I can't. It's a weird pixel count. I think that's a k. Mu sub k n r equals I bar alpha, which is mu sub k mg r equals I bar alpha equals, what is this, a disk? What is a disk I bar? I don't know off the top of my head. The disk homogeneous disk I bar. Berry phases? Hello? Area moment of inertia. I'm surprised that I bar. Oh, it's 2/5 mr squared. Okay. Ooh, good. We can cancel out on r. We can cancel out on m. We have mu sub k times g equals 2/5 r alpha. I like that. What are we trying to find? I already forgot. Number of revolutions. Oh, we need the distance. Okay, so we're solving for the distance, I guess. Oh god. Okay, well, we don't know the alpha. We're probably gonna have to use kinematics or something to get an alpha. Maybe. Yeah. It's gonna equal... Ooh, because we do know the V of the bottom. We can get an alpha. Alright, let's plot along a little bit more. So I'm gonna solve for this, plug in some stuff for this. D equals 1/2 m squared. Oh, I guess I could have left it as I bar, huh? Let me leave it as I bar. Don't look at that. Well, don't look at that too hard. There we go. Okay, so 1/2 I bar omega squared over ff equals 1/2 I bar omega squared over over I bar alpha, like that. So 1/2. How do I do that? R omega squared over alpha. Okay, so we don't know omega and we don't know alpha. So omega equals the bottom of the wheel is what we're gonna say, right? Like V, the contact point. This is gonna be C. Don't. That's not C. I'm getting rid of that C. BC over R. Alpha equals, well, so there's no angular acceleration, it's a constant speed. Const omega. So it's gonna be omega squared R. And the direction, I guess, doesn't really... Then D equals 1/2. I mean, it does matter, but like we're not doing vector stuff here. So it'll be R over omega square. Oh, omega's back. VC over R. Oh wait, I should have just... They're gonna... Fine. It's fine. It's fine. It's fine. 1/2 Uh, I don't know if that's right. Why does everything go away? Does that make any sense at all? It's only rotating. Distance is 1/2 what? 1/2 what? 1/2. 1/2 what? That would mean that, like, for any weight, for anything, it would always move 1/2? It doesn't matter what. 1/2 what? Uh-oh. This is not right. But, like, that's... Oh, wait. No, that's not what alpha is. That's not what alpha is. That's not what alpha is. We don't know what alpha is, actually. Wait, yes, we do. It's I-bar and stuff. Okay, I-bar, alpha. That was just the acceleration that I did. That's why it's wrong. I was really confused. Okay, alpha equals... Yes, okay, it's gonna be based on the MG, it's gonna be based on... Okay, good. I'm using this equation here. That one. Okay, I was so scared. Mu sub k, mgr over I-bar. That makes a lot of sense. Okay. So d equals 1/2 r omega squared over... I'm just gonna say r omega squared times I-bar over mu sub k mg r. So r goes away. That makes sense. That's good. We have 1/2. In this case, it's 2/5, right? So 2/5 m r squared times v squared over r squared. That goes away. Times 1 over mu sub k m goes away. G. Oh, all the 2's go away too. Look at this. 1/5 v squared over mu sub k g. That's clean. That's so clean. That's so cute. It's great. I honestly think that might be it. And then we just need to figure out how many revolutions that is. This would be given in, let's see, what units? We got v squared, so that's, what did they give us v in? Inches per second? Feet per second. So 1/5, 40 squared, over 0.2 times 32.2. This will be in feet, feet squared per second squared, and then gravity is, so this will be in feet. $40 squared, divided by... Okay. 49.6. And then we just have to turn that into rotations. 0.69. Nice. Then we have to say the revolutions of the disk. Okay, radius is 6 inches. So rev equals 2 pi r. Equals, let's see, so that's, I mean, it's pi. Pi feet. It's kind of nice. So 49.68 divided by pi equals, please be right, please be right, please be right, please be right, 15.81. Oh, no, rev. There we go. Perchance. I feel okay, 19.77. It's close. What could we have done wrong? Let's take a look. Okay, let's check this first. Ooh, Damie, I watched a couple movies today. Ooh, what movies did you watch? I've been watching Hades Town in a completely legal manner. Definitely not on YouTube, and you should go watch it because it's really, really, really good. I have like all the songs stuck in my head. Oh, it's so good. It's really good. Poor Things by The Lobster Guy and Gone Girl and Damsel. The Lobster Guy? Who's the Lobster Guy? Let me see. Poor Things. Oh, it's a new movie. I see. Oh. Oh wait, you mean... Wait, Willem Dafoe? Whoa. That looks cool. The one where he becomes a lobster. Oh, I don't know about that. I thought you were gonna say, Huh. What are the other ones? Gone Girl? Oh, I know Gone Girl. Damsel. Oh, that's new also. Oh wait, that's really new. I have not heard of that one. The one where he becomes a lobster. That sounds great. Wait, did I do this right? Let's see. Okay, you wanted to F. Do I have to square anything? Maybe it's not F times D. Oh, great tulip stinger. Is it D squared? I don't think so. I think it's just D, because, yeah, it's just D. Now, okay, maybe it's maybe I'm not checking, because my answer is lower. Maybe I didn't find where it attains a constant velocity. Because the idea, oh, is that alpha equals 0, wouldn't it? However, alpha would equal 0 at this point in time. Which is sort of bad, because then I say that it equals 0. How do I get it to equal 0 without equaling 0? By... Wait, yeah, how do I actually do that? Having alpha be really... No, wait, I need D to equal something. Where what? Yeah, I definitely didn't find where it attains a constant angular velocity. That's my problem. But this is like here. This is right here is the thing. Where did I find this for? I just found it for some time, I guess. But that's really weird that it gave me a value that was like consistent? Because I'm getting... Where am I getting rid of the... Okay, maybe it isn't that. Maybe there's something else that I need to set to 0. Because if I set that to equal to 0, then we would have to say like mu sub k equals 0, which isn't true. Mg equals 0, which will not be true either, and r equals 0. Or none of those things would be true, so we can't set alpha equal to 0. We have to say there's a time when alpha is going to be 0. But I think it'll just kind of cancel itself out. That's what it did. Let me see. Okay. Omega equals V over R? Oh, okay, wait, no, they did that. Sorry, I'm looking at the thing. Angular velocity becomes constant when omega equals V. Oh, because I said omega equal to V over R. That's when we know it's, that's how we know it's correct. Oh, so I just don't need to bother with... Why was I having A in there? Oh, because... Wait, but is there... Oh, wait a second, this is weird. They didn't put a normal force in there. Oh, because that's on the pin. Okay, well, I don't know. That's kind of weird. Sometimes I mean, I guess I can get rid of the pin and say that that's on the pin and not on the... Wait, but that's actually kind of weird. I'm gonna leave this one because I actually am interested in that. Like, why don't we do this pin here? Because when I did it, it's like, oh, you have a pin there, and then you take the moment to find the alpha and it'll cancel. But this seems maybe more... I don't know why you don't do this, because it gets rid of your alpha. Huh. Anyway. That's odd. Kind of fascinating, actually. I'll definitely have to ask about that. Let me just see how many of these there are. Oh god, why is there so many of these? Why is there so many of these? I don't know if I want to... This one looks a little scary. I don't know if I like problems where there are people in the problems. I like it when there's objects, because it feels like I can, like, get away, you know? I'm gonna put a question mark on it. I'm gonna put a triple star. So I know to mark that one for... Actually, let me write it in my question thing real quick. What's up with... I'm gonna say, what's up with the pin? What's up with the pin? Dynamics, problem 1. Ooh, okay. Oh god. Oh, sorry, I'm hitting so many buttons. Okay. 160-pound gymnast is executing a series of full swings on a horizontal bar. A small and negligible angular velocity, and will maintain his body straight and rigid as he swings downward. Essentially, a bar. Oh my god, during the swing, his central radius of gyration is 1.5 feet. How did they figure that one out? Determine his angular velocity and force exerted on his hands after his... Oh, okay, wait a second. Angular velocity and force exerted on his hands? We're gonna have to do FMA after. But we're gonna have to use work and energy to get that angular velocity. I guess, yeah. There's not really any other way to get that. Because, like, we can't do, it's gonna be a force that's accelerating them. Unless you want to find A, and then you want to do kinematics. You wouldn't actually be able okay, you would be able to. If you had an A and you had a V, you could do straight up kinematics. But it would just take longer. Anyway. Sorry, just thought that was important to note. Okay. So this is gonna be impure. I'm just gonna write that. Rotation. I just think it's funny. Of impure rotation. Oh, sorry. Okay. So we'll have T1 plus VG1 My G's kind of look like A's. I kind of want to change that for y'all. VG1 equals T2 plus VG2, and there's no non-conservative forces. At least I don't think, is there? Do I have to worry about the normal force changing? Like an impulse? No, let's not worry about that. It's 0. Through 90 and through 180, so I'm gonna put a datum here. Date 1, 0. And then I guess kind of date 2, 0. This is like 1. At the top, 3.5 feet, so MGH1. I'm gonna try and solve it. I'm not even writing on the whiteboard. Wait a second. I'm gonna try and solve it symbolically. 1/2 MV V squared. We are looking for the angular velocity, so omega is what we want. So plus 1/2 I bar. I'm gonna go ahead and call it k squared m. It doesn't actually really matter that much. Probably won't cancel out. Omega squared plus 0. Alright, I'll do this one as 0. Oh. Bad. There we go, 0. Okay, so I could cancel out an m if I wanted to. Kinda nice. Well, alright. What kind of stuff do we know? We know the height, so that's a known. We know I bar, so that's a known. We don't know the velocity, though, is the thing. Which is... we're gonna have to figure that out through... oh, well, we can just say v equals omega r. So is that true? Let me think. Yes. Is that assuming that his acceleration is 0? I don't think so. I mean, he's moving circularly, is the thing. That's the thing I don't get about the pin, is like, if we assume, like, omega r equals v, sorry, v equals omega r. If we're saying that means that it's 0 acceleration, or did it say constant acceleration? Sorry, let me see. No, it would be 0, constant angular velocity. Oh, you know... But it's an instant in time that we're saying this omega would equal the other omega. I think it's okay. In the other one, we're saying that... That's really weird, though. I don't know. I don't like the other one. Let's see. Let me see if they're gonna assume this. Because if they can assume this, then I want to see why they can't assume it. Because it's actually not a speed. Okay, that's at the beginning. Wait, no. Wait, why is that? 3.5? Oh, wait, no, it is. Okay. Okay, yes. They literally... Wait, they literally said that it's always V, no matter what the... Okay. I'm not sure about that pin problem. That pin problem is a little wacky. But V is always going to equal omega r, is the thing. Right, unless it's like I mean, for pure rotation, fixed rotation, is the word I wanted to use. Okay, mgh1 1/2 m omega squared r squared plus 1/2 I bar. I'm gonna pull out the k squared m. We can just get rid of the m's. And we can pull out an omega squared. Omega squared times I'm gonna r squared plus k squared equals 2ghi. Omega equals 2ghi over r squared plus k squared. Is that right? I think so. Maybe. I mean, I gotta plug stuff in. 2 times 9.8, not 9.8. I lied. 32.2. 3.5 over. Oh, I guess this is actually r. Not that it really matters. It's not something we can cancel out. It is 1.5 feet. If this is wrong, I'm going to be very sad. I mean, it usually is. It's okay. It's supposed to be like 2-ish? 15? That's not correct. What is up with that? Let's see, maybe I just goofed on one little thing. Sweet. That's fine. Wait, I canceled out all the M's. Wait a second. What? Wait, they did this in different steps? Wait a second. Oh, omega squared. Wait, I got it right. I just wrote omega. This is the square root of omega. There we go. Okay, never mind. We're chilling. That's cool. Yeah, 3 point equals 3.94. I was like, that's really crazy. Okay, awesome. Swag. And then I guess I do 180. Or what else am I trying to find? Oh, the force. Doing 180 is not actually going to be that different because I just have to change the values, and that's kind of nice. Except I'm just going to have to... This is not R. I'm going to leave that at H1. It's great to do things symbolically. I can just plug in. Look at this. This is for case 1. This is for case 2. I can just go 2 times 32.2 times, look at that. We can just have our nice answer. Oh, well, a little bit. Oh, I guess I could just multiply by 2. I love the tulip instruments. It's gonna be like multiplied by square root of 2, essentially. Yeah, 5.575. 5.75557. 58. Let's get that in there. Yeah, oh, that's awesome. Okay, never mind. I like doing things symbolically now for problems like this. This is nice. Not that it would be that different. Like, ooh, that's nice. Ooh. Okay. Okay. The force exerted on his hands. We need an angular acceleration for that. But I think there's no. There might be tangential. I'm trying to think about how we would get that. Because we'll need an I-bar alpha. Yes, yes. Yes, very good. Yes. Okay. No, let's just dig around. I'm gonna draw a guy, that's fun. Here's his hand. Draw like a really decent, okay hand, and then just like... I think that's perfect. That's not even... I need to tilt him. We can do the thing, guys. Look at this. How do I move just the center? Oh, there we go. Look. Okay, this is the simulation of this problem. Ready? Oh, he's over. He's going. He's swinging. Oh, he's down. Oh, he's gonna come back up. Oh, he's breaking the laws of gravity. Whoa. Oh, he's going everywhere. Oh, okay. Sorry. Having a normal one today. Okay. Oh no. Escape. There we go. Where's the center of gravity? I feel like right here. And then we have a normal force, I guess. Oh, he got core strength. Have a normal force on his fingies. He's got some... He's doing a flagpole with one hand. That's really impressive. I don't actually even know if that's... Is that possible? Because, like, you kind of have to, like... You would get a moment if you did it like this, wouldn't you? Because you only have one force, you have to have, like, a couple to, like, keep yourself... I don't know. I don't know the dynamics of this guy. What if I gave him toes? Okay, no. Stay on focus. Yeah, somewhat of track. I'll give him a little booty. Yeah, that drastically improved this problem. Is there any other forces? I feel like there's no other forces. Well, I mean, this isn't... Oh, he has acceleration. It's like, this problem... Oh, wait, I have to draw him again. Uh-oh. Okay, we're gonna try and... Uh-oh, his hand... Uh-oh. This is guy 2. That's the FBD. We need the MAD. There's his butt. And his legs. Okay. His butt is a little bit bigger. I don't know, I have to draw the MAX through his butt. Here we go. MAX. MAY. I-bar alpha. There he is. Mr. Angular Acceleration himself. Okay, well, this is not entirely helpful. Oh, I guess MAX equals 0. That's helpful. Okay, I should say the sum of force. Sum of force is X. MAX equals 0. I mean, unless there's a normal force... I mean, there wouldn't really be a normal force to the right, right? I mean, he's not accelerating right or left. Well, actually, he would be, right? Because he's not accelerating right or left, but he's accelerating like to the center because he's turning. I think there might be a normal component here. I think there might be. Because otherwise, how would he not? Well, actually, no, there has to be, because he's accelerating to the center, and that can't come from. Well, wait, I'm thinking in my brain. No, okay. He has an alpha. He has an angular acceleration, which is taking care of the omega in terms of an acceleration of any given point. But I don't think you need the normal force. I don't know. That's like, I think it seems redundant to me. Because if we had a normal force there, what would happen? It would cause an acceleration in a direction, and he's not, but he's like pushing. But if he's right there, which way is he pushing is my question. I think it's this. Let me see what No, there is a 2 reactions. Oh my god. Frozen. Okay. Fine. I don't know why I called 1. We're gonna call it a reaction. Fine. Okay, so I guess we still need to say like all the alphas in terms of omega. Okay, let's just don't worry. You got this. Okay. FX. Or I should do a moment first. Woof. No, I can't do a moment first. I should do a related. Let's do angular acceleration first. Okay, angular acceleration at g equals angular acceleration at a plus angular acceleration at g with respect to a. This is 0. This is going to equal a little thing, 0, 0, alpha g, and the radius, which is going to be, in this case, it's going to be, I guess I could just say r, r0, 0. That's going to equal vectors. They got on me. They got me so bad for not putting vectors on everything. Generally, I tend to label in a way where it's vector until proven not, unless I'm doing something like this, where because I was mixing my I'm not doing it as a vector like here, and then I started working with vectors, I will write the notation. But if I'm only doing vectors, it's like they're all going to be vectors. I'm not going to say vector on each one of them. That's silly to me. Anyway. Okay. Yeah, negative. Okay, so then we have to do... Wait, but then it's just saying AX is nothing. Am I goofing? Yes, I am goofing. There's it's an angular velocity. Minus omega squared. Minus omega squared. Oh, we just found omega. I say negative alpha g times. That's not that helpful. I'm not gonna say that. I'm gonna say it like this. We're gonna write it like this. Negative r is 0 minus omega squared. R is 0, 0. And then we say a big one where we put it all into it and I fix the signs. Alpha g, 2 alpha, r alpha g. 0. Don't know why I did that. Negative omega squared r. There we go. So now we have max and may in terms of alpha. We can do our moment about r equals I bar alpha plus r may. Let me check the sign on that. It is plus r may. And max goes away. Although it wouldn't go away the next time we do it, but whatever. So the moment is going to be negative mgr equals I bar alpha, and then plus r times r alpha g. So negative mgr minus alpha, oops, factor out an alpha, r over, let's see, I bar plus r squared equals alpha g. How do you feel about that? You know? What was I trying to find? Oh, the reactions. Okay. Well, I mean, the MAX one is easy. We could have found that one years ago. I think after I do this one, I'm gonna take a break. Because this is actually not due for a little bit, but I do want to get it done a little earlier if I can. But I still have to do EE and CE today. Not on stream though. I'm gonna do them off stream. Because I'm gonna come back and do big reviews on them. But you know. Well, maybe I'll be able to do something else. I don't know. Whatever you guys are up for. If you want to listen to me cope harder, then I could do another one. What was I doing? I can probably factor an R out of that, but I don't really need to do that. Oh no, I can't. I lied because it's they turned him into a circle, so we can't get an R. We only have a K. Okay, we have an alpha G. That's great. Now we can do some fx, fy. What are we feeling? Sum of forces in x equals max, which is going to give us rx equals m times negative m r squared, which is just something we can plug in, which is great. What is that? That's 160 32.2 times omega squared. In this case, it's we'll do it for the first case. 3.94 squared times our r, which is going to be 3.5. This number's looking a little bit big, just from what I'm seeing. But who knows? Maybe it'll turn out in our favor. Now, this is a force, and he has 160 pounds, so, you know, it's gonna not be... 2,703 sounds very wrong. What is up with that? This guy's got 2,000 pounds of force on his fingies? That's not happening. Hello? Did I get my omega wrong somehow? That's not even the alpha. That one should just be right, is the thing. Is my radius not that? What's happening? What's happening to him? He's it's like that's not it, I don't think. Like 3.9, that's like, okay, let's say that's like 4 squared, that's like 16. 16 times 160. Um, hmm. I think the 3.5 is not gonna be an issue. Why did they give the distance to his other? They gave 2. Oh, you guys can't see that. I'm looking at this. They gave like the other 3.5. Oh, probably for the bottom. I was like, why do we need that? That's interesting. AA is going to be 0, so that's not an issue. Alpha G. This is very standard, this deuter right here. I mean, that's like the most standard acceleration you can get. That is straight up angular acceleration for a fixed axis rotation. Just like generally. Maybe it's this, maybe it's this. So I bar alpha G. No, but it shouldn't matter because it's our MAX. I don't, wait, is it right? There's no way it's right. I might have just had a sign, like a little thing, like a, whatchamacallit. Maybe I just got it, did I put in a 0 somewhere is what I meant to say. It's 35? Wait, did I just say 35? Well, we found the issue, folks. I multiplied it by 10. That would do it. You know, if you ever feel bad, ever feel like you're not good at math, or you're not good at physics, it's okay. No one is really that good at anything. Even the one of us who is doing things with it. Execution is a funny double entendre for how I feel about what calculations do to my brain. I'm gonna start drawing myself like a wizard in every drawing I draw, like with elf ears. It's just a tear. Wait, I have to have my wizard beard. It's not a wizard beard, that's just a regular. Wait, I have to draw my wizard hair. My outlandish wizard hair. My hair's actually getting kind of outlandishly wizardy in real life lately. But it's kind of great. It's kind of like where I want it to be. I'm not gonna do big angry eyebrows. Thanks, Obama. The cookie, that's a... They're just some phrases that reside in my head, you know? Like the Joe Biden bearing dogs meme. Like, how would I ever explain that to somebody if I just referenced that accidentally? You know, it's just such a common thing in my life. It's not common. I do think about it though. It's not very rarely. Anyway, we have to do FY. casual numbers. You know, my mic exploding just really sells it home. Maybe my mic only explodes when I do calculations, because that's the only time it's exploded this whole stream. 160 divided by 13.2 squared times 13.2 times 3.5 squared. This one is a big number. Okay, that's a little big, I think. 415? Okay, it's actually not that bad. I don't know why I added so many significant figures there. 416 is fine. Like past that point, you're getting into like the thousands of the inches, and we're not manufacturing stuff here. Okay, so it's not that. Oh, it's because I forgot the weight. You know, classic. You know me, just not looking at things and just not writing things down correctly. That's why I feel like this. That's why I feel like this. Here, we'll do that. I feel like that better encapsulates my feeling than a tier. It's more just like me being like, here, wait, if we did this and this. There we go, now it's really accurate. Now I'm like mad and weirded out. Okay. I don't know if that math is right, but like 416, it's not right. I just saw what it was and it wasn't that. Maybe I calculate this first. What is it? Okay. Oh wait, MG, what am I doing? Why am I, okay. 160 times 3.5 divided by 1.5 squared times 160 divided by 32.2. Okay, I need to put another parentheses in here. Gosh darn it. Gosh darn it. Plus 3.5 squared. Is that right? Okay, yeah, 23.9 is alpha G. Oh, sorry. So then we have 23.9 times 160. Oh. Times 3.5 times 160 divided by 32.2. 415. Okay, so it was right. And then this minus 160. But it's not going to get me what I thought it was going to get. 255? That's like big. Oh, my alpha is wrong. Oh wait, that's for the other one. Whoopsies. I know it's not. Oh no. What's up with this? If I or positive, it doesn't really matter what it is. Oh, well, it also doesn't matter. It's 27. I got 29. Oh, that shouldn't. Or no, I got 23.9. Which I don't know why. Where did I get alpha? Yeah, alpha. Okay, let me check my moment about R. Negative MGR. And then I guess I should say negative alpha. Does that matter? Oh, it does matter. That one matters. Signs matter, y'all. And then the R for the MAY is actually positive. This one's negative, so this one's going to be subtracted from it. So So it should make it... bigger? So that's definitely wrong. Was R squared? I was close from before, but also, like, where was I going wrong? Am I going wrong here? Because my MR... My MAAY is wrong, but I kind of doubt that's wrong. And AY is going to be from the centroid, so we have a distance of R, so that's chill. Fascinating. Is my I bar not right? Did I just like use the wrong value for I? No, it's 1.5 feet. Let me just try calculating one more time. We'll try that. So 160 times 3.5 divided by 3.5 squared minus 1.5 squared times 160 divided by 32.2. Yeah, it's really big. That's probably because it's such a small number. So unless... Yeah, so 30, okay, so that's right, and then... Wait, 160 divided by 32.2... Wait, are they not using... Wait a second. Oops. What is with this 32? Oh no. A squared. Okay, that's the k squared m. Theirs are both plus. Am I saying that MAY rotates the wrong way? Oh, I guess. Okay, that's why. Because I can't say it rotates downward and accelerates upward. That's not possible. What is easier to fix? This one's easier to fix. It has to go down, which means it would be positive. The thing is, it was still off when I did it. I don't know that. So this one will be positive, and this one will be positive. Or this one will be negative. It's the better thing to say. That's negative. Not the better thing to say, the correct thing to say. But so, why is it not right, though? It still says 23.9. Literally doing the exact same numbers. Gamers. What is up with that? Wait, they say it's 7. 3.5 squared. Wait, did I forget an m? No, that's r squared. What's that? Wait, maybe I forgot an m. Oh, I forgot an M. I literally just forgot to write the M. God. Wait, but then everything is an M and I can just cancel it out. So it's just 32.2 times 3.5 divided by 3.5 squared plus 1.5 squared. 7.7. Okay, that's where I like went crazy wrong. There we go. Okay, we figured it out. That's why this is all goofed up. Okay. I mean, there's an easier way of doing this also. Just get rid of this and don't do this. MR equals 7.77 times 160 divided by 32.2 times 3.5. And that's going to give it to us. And we've solved the mystery. Yes, minus 160 is 24.4. 24.8. Let me say minus 160 equals 24.8 pounds. Close enough, I think. It actually, is it exactly? Yeah, 24.8. Perfect. Great. Alright. Yeah, so I just forgot an M, you know, just forgetting to write things, forgetting the directions of things, not things that we just need to grind. And that's why I'm just going to be doing a bunch of problems from now until Monday, which is my final. Wait, not next Monday. No, not this upcoming Monday. The Monday after that. God, if I was going to the final now, I would kind of be screwed because there are things we just haven't learned. Should I don't want to work on this one anymore. I don't want to do this for the second case. What if we just did another one? I got time. Where do I have to be? Nowhere. Let's go for it. Let's do another one. Let's see if we can mage it up to be a little bit. Ooh, this one is symbolic. This one's symbolic. Yes. Less math, less calculations I have to do. Okay, the goal. Here's my goal. Wait, I'm gonna draw my wizard goal. I just love. I was thinking of a metaphor. My wizard goal. My big wizard arms. My wizard hair is all like, wah, because I'm like, I'm wizarding. Wait, this one's look a little bit more mad. A little bit more like I care about anything, maybe. There we go. Okay, wizard goal. Read. Yeah. And write down all things properly. I was gonna say my my sort of analog, I think, to the issues that I have in dynamics kind of stuff is, I think it's kind of funny because it's like if you were a really good wizard, right? But then it's just like your spell handwriting was just really bad, and so your magic circles got like really squished at the end, and it just made them completely ineffective because they just got so squished that like it didn't work. But you're writing down all the right stuff. It's just like you're trying to like get better at just like partitioning things out. You're not really getting better at doing the magic part of it. For me, it's like I'm fine at doing the dynamics part. I just forget to write shit down sometimes, or I just like put things in the wrong. Okay, putting things in the wrong direction is more of a dynamics issue, and like knowing that, like seeing that is something you need to be able to be good at dynamics. I'm not counting that, but I'm counting just like me not writing down the M. Like, okay. Oh, this is such good wizard music too. A rope is wrapped around a cylinder of radius r and mass m. Knowing that the cylinder is released from rest, determine the velocity of the cylinder after it is moved downward a distance s. Okay. So we have a cylinder. Let's do working energy, so we know it's that because we're doing that. State 1 is going to be up here. So V equals 0. And state 2 is going to be down here. We're going to call this S. Make it a little, there we go. V equals what? We don't know what that is. Now, it's also going to be rotating because there's a rope wrapped around it. Which is great. Love that. I don't know. This is a good problem. I like it. Okay, this is actually great too, because like, so our guiding equation is going to be delta T equals delta VG. We don't have any friction. I mean, it doesn't give us a coefficient of friction. Can't really do anything other than that. So, we are going to have to do some related velocities and acceleration stuff, but, you know, other than that. Okay, let's see. 1 second. Let me get in the mindset real quick. Okay, I'm ready. I'm magicked up. I'm gonna write everything so diligently. Alright. T1 equal T1 plus I already messed up. T1 plus VG1 equals T2 plus VG2. Okay, now where do we want to set our datum? I'm kind of saying we should set the datum I'm kind of feeling we should set the datum at the start. No, I lied. Let's set it at the end. I just thought about doing everything in negative, and then I was like, that's gonna mess me up. So we're gonna say datum 0 there. So this one is gonna be 0. I know it's gonna make sense, like, as it falls, it's positive up there and 0. Yeah. Okay. So T1, 1/2. Sorry, T1 is 0. Release from rest. Okay, so MGS equals 1/2 MV squared plus 1/2 I bar omega squared. That's it. Okay, now it's a cylinder, so we know it's I bar. And we also know that V is going to equal omega R. Yeah, maybe. Oh, sorry. Maybe let's just solve for the velocity of the center of gravity. Let's just solve for that first, and then we can kind of move things around. Alright, so V squared equals MGS minus 1/2 I bar omega squared divided by M times 2. Now, is that gonna mess me up if I leave the 2 there? What if I put a 1/2 on the, let's just put a 1/2 on the bottom. Also, I'm gonna put the square root just now, because I forgot it last time, so let's do that. But I already wrote the square there, so that was fine before. Okay. So what do various things equal? Actually, I'm looking at this, we shouldn't do it like this. We should solve for omega, because right now we have, sorry. Can I explain CSMA? Let's see. Let me take a look-see. CSMA. I may not have, okay, okay, carrier sense multiple address? Oh god, this seems actually like I might not be able to explain this. I'm quoting from Wikipedia. It is a medium access control protocol in which a node verifies the absence of other traffic before transmitting on a shared transmission medium. Oh, it's a protocol. I actually don't really know that much about, like, protocols. But, it just kind of seems like it just is like looking both ways before it crosses the street. I don't know how to do it, but it seems like it's just making sure that nothing else is there before it goes. I don't know if that answers your question or not. Okay, I'm going to turn V. V's gonna equal omega r. And we're gonna see if we can solve for omega in terms of stuff, and then we can kind of back out a V. So let me get mgs equals 1/2 m omega squared r squared plus 1/2 omega, or I bar omega squared. I'm gonna switch the sides. Probably gonna mess me up, but I'm just gonna keep saying that. If I say that to everything, then it won't mess me up. Okay, so omega equals mgs over... I'm not gonna do that yet. This is a cylinder, so it's 2/5 mr squared. M. Oh. Do you see what I see? Check this. Omega squared, r squared, 1/2 plus 1/2 times 2/5 equals gs, b squared. Yeah? That's kind of cool. It's kind of cute. Times 1/5 plus 1/5. So gs. What is this? This is, we do tenths. Uh, 5 plus 2, 7. Or 10 gs over 7. Unless I messed up my cylinder I bar, let's check that before we do anything else. Area, moment of inertia, cylinder. I think we did it earlier and it was 2/5, right? Oh, it's 1/2. And that's why you check. That's why you always leave a note. 2/5 is for a disc, I think. Not that I have to memorize that, so it's not really a big deal, but oh, that's so clean now. Look at this. What? You can't smoke until you're 18. 3/5. 3/4. What? So 1/3, 4. 4/3? I like that. Let's see. Okay. I'm gonna check with my maid magic. Let's see. Okay, we set everything up. We got the states. My goal up in the top. Did we read it? Okay, let's check if we read it correctly. It's wrapped around a cylinder. So that means it has an I bar alpha thing. Knowing that it's released from rest. Okay, we started to release from rest. Determine the velocity of the center of the cylinder. We solve for the correct thing. After it's moved downward to distance s. We move downward to distance s. Okay, good. Let's check. Don't have any elastic potential. We're chilling. The first starts at 0, and then we set our datum correctly. MGS, that's how much up we are, equals 1/2 mv squared plus 1/2 I bar alpha, I bar omega squared, equals omega r. I guess we could have just said omega in terms of whatever. I like this better. So we have omega squared r squared, and everything else is the same. We didn't drop any terms. Filtered this out. Factored this out. Got in there. Nice. Clean switch. Okay, we get rid of the m's on everywhere. 1/2 mr squared. We got that, and times 1/2. We got that. Extra 1/2. We pull out an r squared. It seems pretty clean. I mean, it's not that hard. I swear to God, I'm gonna like look at it. It's gonna be like, no. Let's go! Let's go! 4/3. Let's go! Yes! Big win for evil magic users. Big win. Yes. My magic, it grows. I'm just glad I wrote everything down right. We do the gamers. Okay, it's actually a pretty easy problem, so maybe I shouldn't be celebrating this hard. But like, we got it. And I checked the I-bar thing beforehand, like... You know what, actually you know what, it's good to celebrate wins. Even if it's a small thing. Even if it seems easy, because not everything is easy for everybody. And if something's hard for you, that's okay. And it's okay to celebrate it, even if everybody's like, adding 2 numbers is easy. You want to celebrate it? You should go ahead and celebrate it. It goes for anything. I'm gonna draw a little better hand in celebration. Yes. That's pretty great. Okay, that was actually a very easy question. What time is it? Oh, we could do one more. Maybe I'll go at 6. Let's do that. Or maybe, okay, it might be a little earlier than 6. Maybe I'll just set up the next one. Oh, this one looks a little wild, maybe, perchance. This is like the other one, but actually this one I feel like we could have success on. I feel like the summoning circle. This one I'm gonna put a big plus on. For me getting it right on the first try. I like to have little markers for my own. I can kind of visually see in my layers when I have a lot of layers in this document. I'm gonna have to switch it over sometime soon, but I guess I'm almost done with the quarter, so it's kind of when I switch my documents. Oh, the next one's gonna have so many because I'm doing thermal and fluids probably. Or fluids and linear. Yeah, we'll get there. We'll cross that bridge when it gets there. We gotta do dynamics. Okay. States. I'm just gonna set up the states, I think. That's really easy. Maybe it won't just be setting up the states. There's one. Rolls without sliding, we got friction. After it's rolled through 90 degrees. And the reaction at the surface. Oh, that's great. I love when it's not making me do a bunch of bullshit. Okay, so O is gonna be there. Like a watermelon. Let's put the datum here. Playwright datum. Alright. Maybe we set up the, so the thing about this one is we do have to include friction, which is gonna be a little annoying, but, you know, I think it's gonna be okay. Because we're gonna have a distance that's known based off of the, radius of the cylinder, right? At the beginning, delta t equals delta v g plus u1 to 2. This is gonna be like 4 G, because we want to do it for the point G. Now for G, it's not really the point G. Like when we're doing the object, we're using its centroid to sort of locate everything. G2 plus VG2 plus U1 to 2. Prime. Yeah, okay. Okay. Maybe I can just write out these two, and then we'll be done. Okay, sorry. Let's just check. Release from rest. Oop. Gravitational. You know what? Let's not choose the datum here. Let's make it at the bottom. Why are we making our lives harder for ourselves? Maybe a little bit wacky when we have to say the distance from here, but like, whatever. Kind of would, yeah, that's fine. It'll be like r minus 4r over 3 pi. So that's fine. This will be 0 then. Right, so we have m, g, and now we instantly have to do the thing that I just said. For... Oh wait, no, it's not that. It's just 4r, because they give us the distance of geo. That's nice. 4r over 3 pi. And that's going to equal 1/2 m v squared plus 1/2 I bar alpha omega squared. And then plus ff times delta s, which is going to be, I'm just going to say, so this is like, this is f delta s. And we're going to say that's 2 pi r times, now how much has it rolled when it's rolled through here? Rolled through a quarter of the circle. 1/4. There we go. I mean, I guess it tells us 90 degrees as well at the top there. Alright. And then from there, you know, we'll just go and say RV is equal to omega squared. We'll do FMA to get some information about our friction force. And then we'll be able to find, yeah, angular velocity. Really, I think the biggest thing here is like knowing that V can be expressed in terms of omega. If you didn't have that, you would kind of be stuck with too many variables. And also making sure that you include your relative stuff in your FMA for anything with friction. Because if you don't do relative stuff, then you're gonna have a bad time. To say the least. You're gonna not get the right answer. I should make a wizard outfit. Oh, I want to make more outfits. I was gonna make one for New Year, but we'll get there. Maybe I'll just make it for, I mean, what is the name for Lantern Festival? It's like, it's not spring, because Chunjie is New Year's. What's the lantern? It's like, Guangdong, maybe? Maybe I'll do it for that one, though. Lantern Festival. What? Wait, it was February 24th? Wait, I thought it was in the spring. Oh, Yuan Xiaojie. Wait, what? I did not realize it was during New Year. Oh. Me not knowing my Qixi. Oh, Qixi might be. Oh no, that's like Valentine's Day. Why is it August 10th though? Maybe I'll do it for Valentine's Day. Or, I don't know, I'll just do it for fun. I'll just be like, whoopsies. A wizard outfit would be good too. Alright, I'm gonna be back probably pretty soon. Probably pretty soon. Probably, trying to think. I try not to stream 2 days in a row, so I'll probably be back Tuesday. Any time where I'm not back Tuesday? No. I would be back Tuesday. I don't think we're gonna be well, we might do CE. Maybe I'll do that because it's a good review because it's kind of like everything, but also it's just like probably better to do dynamics. Anyway, I'll see you guys later. Thanks for hanging out. It's nice to have some company when I'm going insane. But you know what? We gotta win on an extremely easy problem. I'm so mad because this problem is so easy. But like, I mean, this one was also pretty good. I just like didn't the numbers. This one was weird. This is the L. This is the L. Aw, big heart. Thank you, Unstucky. So sweet. I gotta catch more of your streams. I'm gonna be real, I have not sat down and watched a live stream in like a long time. I usually try to catch VODs now, just because my schedule's all over the place. But it's always nice to see you around when I do get to see you on stream. Yeah, with that I'm gonna head out. I'll be back probably Tuesday. If not, then Wednesday. I really doubt that I would wait that long because I got stuff. I might as well do it on stream. Talking out loud to myself, you know, good for the brain, good for the heart. Honestly, if you want to watch one stream, I'm gonna be on Tiny Toxic Tofu next Monday. What time? I do have a final on Monday. If it's in the evening, I will not be able to do that. My final is at 7 p.m. at night. PST. But if not, 1 p.m. Eastern? 1 p.m. Eastern. Oh wait, I can definitely do that. But yeah, I can do that. That's like early. Oh lol, definitely not that. Yeah, wait, just let me write that down somewhere real quick. I'll put it on my calendar. Monday. What time is it? 1 p.m. So that would be, let's see, 10 a.m. for me. What are you guys doing? Gaming? What did I say? 10 a.m. Yeah. Wiggle away. Oh, podcast guest. Wait, that's so fun. That's great. I love listening to podcasts. Wait, that actually is like awesome. I love that because I can just listen to it and I don't have to like actually watch something, and that makes it a lot easier for me. Cool. I'll be there then. Or if I can. I mean, there's a small chance I can't, but I'll probably be able to be there. I will definitely stop by at least, for sure. Alright, I'm gonna head out now. Bye everybody, see you later.